Today's video, we're going to look at the last part of Chapter 15, Equilibrium, and it deals with this thing called Le Chatelier's principle. Let me scoot back a little bit. Okay, now, as I said yesterday in the video, Le Chatelier's principle is the easiest part of equilibrium. So what does Le Chatelier's principle state? Well, it says that if a system at equilibrium is disturbed by a change in temperature, pressure, or a component's concentration, the system will shift its equilibrium position so as to counteract the effect of disturbance. So what that is telling us is that when we look with these problems, when we're looking at a reaction, it's already at equilibrium, then we're going to change something to see which way the equilibrium is going to shift. It might shift left, it might shift right, or there might not be a shift change whatsoever. So if we look at those different things that we can change, temperature, pressure, concentration. So if you look at concentration, if we increase the concentration, equilibrium will shift to the opposite side of the reaction. Now what I did was I went ahead and wrote down all the information and everything. Then we're going to look at an example of a Le Chatelier's principle problem and see which way it's going to go. If we have a decrease in concentration, equilibrium will shift to the same side of the reaction. Now the next one, pressure. Now along with pressure we have volume. And the reason why, if we go back to our gas chapter, we found that if we have an increase in pressure, volume will go down because they are inversely proportional to one another. So if we have an increase in pressure, that means we have a decrease in volume. Equilibrium will shift to the side with the least number of moles of gas. If we have a decrease in pressure or an increase in volume, equilibrium will shift to the side with greater number of moles of gas. Now the third thing, temperature. Endothermic, well, if we have something that is endothermic, I wrote those down wrong. Endothermic heat would be a reactant. I completely messed that up, I apologize. And if it's exothermic, heat will be a product. Now, how do we know whether it's going to be endothermic or exothermic? That information will be given to us. So if heat is an endothermic reaction, our delta H, change in enthalpy, will be greater than 0. And if it's exothermic, then it'll be less than 0. I do apologize, I'm going to write. Okay. So if we have an increase in temperature, equilibrium will shift to the opposite side of heat. And if it's a decrease in temperature, equilibrium will shift to the same side of heat. Now, one more thing that we can possibly do to a reaction. What if we add in a catalyst? Well, we learned with kinetics, catalyst just lowers the activation energy or it speeds up the reaction. If our reaction is already at equilibrium, adding a catalyst won't even change the equilibrium. We won't have a shift whatsoever to the left or to the right. So our example says determine which way the equilibrium will shift in the following reaction when the following changes take place. So here's our reaction. N2O4 yields to 2NO2 and our change in enthalpy, delta H, is 58 kilojoules. So it's a positive number. That's telling us that heat is a reactant. Okay, so it's going to be on the left-hand side. So let's kind of look at these different scenarios and see which way equilibrium is going to shift. So N2O4 is added. Well, if we add in N2O4, that means that we are actually increasing the concentration. And if we look back here, it says increase in concentration, equilibrium will shift to the opposite side of the reaction. N2O4 is on the left-hand side. So the equilibrium is going to shift to the opposite side. It's going to shift to the right. It's trying to compensate for the more on the left-hand side. Now let's look at B. NO2 is removed. All right, so if we remove NO2, that's a decrease in concentration. Decrease in concentration, equilibrium will shift to the same side of the reaction. So NO2 is on the right-hand side. This is also going to be a shift to the right-hand side to compensate for the decrease in the concentration. Now C, pressure increased by addition of N2. Okay, well, we have an increase in pressure, and if we look back here, an increase in pressure, equilibrium will shift to the side with the least number of moles of gas. But if we also look at the other part of this problem, by addition of N2, we don't have N2 up in the reaction. It's an N2O4, but it's not by itself. So this is kind of like adding in a catalyst. We will have a no shift change for this one because in nitrogen, just N2, is not part of the reaction. All right, let's look at our next scenario. Volume is increased. Okay, so if we have an increase in volume, equilibrium will shift to the side with greater number of moles of gas. Well, to figure that one, we have to look at our balanced reaction. Over on the left-hand side, we just have a coefficient of 1 in front of N2O4. Right-hand side, we have a coefficient of 2. Which number is larger, 1 or 2? So hopefully you figured out that it's 2. So with the volume increase, we will have a shift to the right-hand side. Okay, now our last one. Temperature is decreased. Okay, so if we look back at what we talked about with temperature, equilibrium will shift to the same side of heat. Well, now we need to figure out, is it exothermic or endothermic? When we said that our change in enthalpy was 58 kilojoules, a positive 58 kilojoules, so we said that heat was on the left-hand side. So if temperature is decreased, it will shift to the same side as heat. So this would be a shift to the left. Okay, well, I hope that these videos are helping you out and everything. This should help you out with the rest of the assignment. If you have any questions, please let me know, and I will respond back as soon as I can. I hope you're having a good day, and I will talk to you later. Thank you.